All right, geometry students, I promised to have an ending to this video so you're not left wondering if I forgot something or if something got cut out. Two lessons that we're going to do today, but we've already kind of begun them, so I don't think it'll be too hard to get through this in one 45-minute class on Monday. First is this idea of CPCTC. We've talked about what this means. This is the same thing as the definition of congruent triangles. This is powerful because it allows us to go from congruent triangles to congruent parts, or from congruent parts to congruent triangles. What we usually, or what we normally use this for, is once we know two triangles are congruent, we're usually wanting to get their corresponding parts congruent. So I've used this example before. This is a shape we'll study later called a parallelogram. And the definition of a parallelogram is that the opposite sides are parallel. That's it. There's nothing else that is inherently defined by something being a parallelogram. But if I introduce this diagonal segment, what I can say is because I know the opposite sides are parallel, I get alternate interior angles there. I get alternate interior angles here. And then I get this shared side. And so I can actually prove that these two triangles are congruent, which isn't that important, but then the corresponding parts that I don't know are congruent, I can say are congruent. So I can get the opposite sides of the parallelogram are congruent. I can get that the opposite angles of the parallelogram are congruent. Because the sides are parallel, it's pretty easy to prove that the consecutive angles are supplementary. So we use CPCTC, or the definition of congruent triangles, to get other things congruent after we get the triangles congruent. So that's really all 4.6. That's what we're going to talk about. How could you get these parts of triangles congruent? What triangles would you have to get congruent to get that? Don't forget, the ways that you can get triangles congruent are SSS, SAS, ASA, and AAS. You can say all those backwards, and the only one that looks different is this last one. It looks like SAA, but that's totally fine. And then in some cases, you can use hypotenuse leg, and that's when you have a right triangle. If you don't have a right triangle, or two right triangles, you can't deal with hypotenuse leg. The sixth way is the definition of congruent triangles, but to get all six parts congruent is usually impossible or very difficult. And sometimes what you're trying to prove is that parts are congruent, so you use one of these shortcuts, so then you can say the corresponding parts of congruent triangles are congruent. So while the definition of congruent triangles can be used to get triangles congruent, 99.9% of the time you will be using one of these shortcuts. Good? So that is 4.6. So that should go pretty quickly. On Tuesday, you're going to get a proof packet dealing with a lot of 4.6 and 4.7 stuff and all of Chapter 4 stuff. The next lesson, 4.7, talks about isosceles triangles. And we've also done this before. So if we take a look here, we have some definition of terms that I may have glanced over, but I need you to know. Remember that an isosceles triangle is any triangle with at least two congruent sides. When we have exactly two congruent sides, we call those two congruent sides legs. And the angle formed by those sides is called the vertex angle, and the side opposite the vertex angle is called the base. And then we have what are called the base angles. So just some terminology, some vocab. We've already proved these two theorems in class. Remember the base angle theorems, I call the isosceles triangle theorem. You will probably write if sides congruent, then angles congruent. I think that's really the best way to write that theorem. The converse, if angles congruent, then sides. I really want you to write it this way, Parker. I hope you're listening. I don't want to see base angles theorem. I don't want to see converse of the base angles theorem. I want to see the logic I know I have sides congruent, so I can say angles congruent. Or I know I have angles congruent, so I can say sides congruent. I don't want to see the names of these theorems in proofs that you're writing. I think it just, for me, I think it makes more sense to see what you're actually using in picture form. Two corollaries to these theorems that you've already proven here. If a triangle is equilateral, then it's equiangular. If a triangle is equiangular, then it's equilateral. That's just an idea that I think you'll need to know. I would not be upset if you wrote it this way: equal sides if and only if congruent or equiangular. I think it's kind of nice to write it this way. Again, I don't love the names of these theorems. Your homework or your classwork on Monday is going to just be a lot of algebra practice setting these equal together. Algebra 2 students, I may fold in some quadratics for you so you get double review. Wouldn't you love that? Okay, thanks for your patience. Sorry this took so while to get up. Long weekend. Thanks to all of you who helped out. Even the guys who didn't have to, Joey and Ten and Daniel, nice work. Philip, although Philip, you're not watching this geometry video, but shout out to all of you. Eli Conley as well, being a presence in the dorms. You guys are awesome. Much appreciated. Have a great rest of your Sunday. Peace!